right, folks. So picking up where we left off yesterday, we were talking about energetics and reactions. We were talking about how we have endothermic and exothermic reactions. So if we see this if we look at this energy diagram and we see this as a forward reaction going this way, is this endothermic or exothermic? It is endothermic. That's right, Brent. Because we are adding energy. We are putting energy into it. So if I was doing this in a beaker and I picked up the beaker at this point in the reaction, what would it feel like? It would feel cold, yes, because we have taken, that energy is coming from the heat of the surroundings. That's where that energy to get up above our activation curve and then to get to our higher energy products is coming from. So it would feel cold. If we did this in reverse, if we started here, we would still have an activation energy hump. It would be smaller, and our products would be lower energy than our reactants. So our delta H going backwards, would that be positive or negative? It would be negative, right, because it would be our final minus our initial, and that would be a negative, because our final product would be lower, have a lower enthalpy. Okay? So when we are measuring the heat and the energy that's transferred in reactions, how do we do that? Well, one of the biggest equations that you should probably memorize is looking at the heat released or absorbed in a reaction using Q equals MC delta T. So let's break this down. Q is a variable that we use for heat, which apparently we need more of in this classroom today. You're not the only one who's been going for the blankets. It's sometimes written lowercase and sometimes written uppercase. I honestly couldn't tell you why it's sometimes lowercase and sometimes uppercase. More often I see it the uppercase Q, but in terms of chemistry, that's really the only Q that we use on a regular basis. So it kind of doesn't matter. It's not like molarity where like lowercase m is molality and uppercase m is molarity. So Q is the heat absorbed or released, and that's going to be measured in joules, which is our SI unit for energy. Yes, it is. Yeah, it says page 5 at the top. Yeah. So in that area, in that calorimetry stuff. Calorimetry stuff, yes, brilliant. Okay, I'm so much more self-conscious about what I'm saying now that I have this microphone on. All right, so and we're going to do some calorimetry tomorrow at the lab benches, okay? So you get to see what that looks like, how it works. So our M, so we've got Q equals MC delta T. Our M is going to be the mass. All right, it's going to be the mass in grams of either the solution that we're measuring the temperature of or the object that we're measuring the temperature of. It depends on what we're actually measuring. So a lot of times these reactions are going to be happening in solution, and the mass is going to be how much of the solution do we have. If we have less solution, it's going to take less energy to change the temperature. Okay? If we want to heat up the ocean, it's going to take a lot of energy. If we want to heat up a mug of water for tea, it's not going to take that much energy. Okay? So mass of the solution is going to be in grams. C is a quantity called specific heat capacity. All right? That is something that you need to know what it is. C is specific heat capacity. So heat capacity, we can think of it as how difficult is it to change the temperature. Okay, for some things, think about when you were a kid, if you ever went out to a playground on a hot sunny day. Were there any parts of the playground that you didn't really want to interact with on that hot sunny day? The metal slide, yeah, that's the classic, right? Metals have a very low heat capacity. It's very easy to change the temperature of a metal. So when they absorb energy from the sun, they get hot very, very quickly. Okay? There's one thing that has a very high heat capacity, not the highest, but one of the highest, that is incredibly important and is the reason why people like to go to the coast in the summertime. Water, okay? Water, what did you say? Well, the sand probably has a relatively, compared to metals, is going to have a relatively high heat capacity. It's going to take a lot more energy to heat up the sand than it would a metal. But water has an extremely high heat capacity, okay? And so it's super important for life. It's super important that it takes a lot of energy to change the temperature of water because there are so many things. Think about our bodies. We have all these enzymes and other chemical reactions happening in our bodies that have to happen at certain temperatures. If our bodies were as easy to change the temperature of as the metal on a slide in a playground, then our temperatures would be all over the place, and it would be impossible to regulate all those reactions. Okay. Also, it relates to how ocean or large lakeside areas are cooler than the inland areas. When I lived in Chicago, I lived in an area that was just a few blocks from Lake Michigan, and it was always much cooler there than it was just 10 minutes drive to the west. Okay, and that is because water is absorbing some of that heat from the atmosphere, but the water itself is not changing its temperature very quickly. And there's a lot of water, yeah. Yeah, Brant? Between what? Oh, no, that's different. But you couldn't really have functional cold-blooded animals without the specific heat of water being so high. So we do a lot to regulate our heat, warm-blooded animals do. Cold-blooded animals have to absorb the heat from the surroundings more, but if the specific heat of water wasn't as high as it was, they would lose a lot more heat energy to the surroundings faster in environments where they don't have the sun or their heat rock or whatever. So yeah, it is related, but not in the sense of distinguishing between the two. Okay, so specific heat is going to be a complicated constant. It's going to be a constant for each different substance. So water is going to have a specific heat. Each metal is going to have a different specific heat, and we might get to test that tomorrow. I haven't 100% decided the format of the lab, but in any case, so the specific heat capacity is going to be in joules per grams degrees Celsius or joules per gram Kelvin. All right, so in our lovely IB format of putting things in the denominator as -1s, so writing it out would be joules per gram degrees Celsius or joules per gram Kelvin. And you'll understand why when we put the rest of the equation together. Okay? Delta T. Delta has a number of meanings in a lot of different fields. Most of the time, it's change. It symbolizes change. Okay, so it's going to be the change in temperature. So the change in temperature, again, it's either going to be in Celsius or Kelvin, and which one that is going to determine or depend on what units you have your specific heat in. Okay. So the change in temperature, as with everything, is going to be the temperature final minus the temperature initial. So sometimes that's going to be a positive value. Sometimes that's going to be a negative value. Okay, if we are decreasing temperature, our final temperature is going to be lower than our initial. We're going to have a negative delta T. If we have a negative delta T, we're also going to have a negative Q. If the temperature is going down, we are losing heat. So it all kind of makes sense. Yeah, Lukuba. That's a good question. So if it's an exothermic reaction, is the final temperature going to be higher or lower than the initial temperature? So if it's exothermic, so our final enthalpy is going to be lower, okay? So the enthalpy of our products is going to be lower than our reactants. But that heat is going to be lost to the surroundings, and we're going to experience that as an increase in temperature. So if I have an exothermic reaction in a beaker, and I touch that beaker, the beaker is going to feel warm. It is releasing heat into the surroundings. The temperature of the solution inside that beaker is going to be warmer than the air outside, which is why it's going to feel warm. Eventually, as the air outside absorbs that heat, it's going to reach thermal equilibrium, and it will feel like room temperature. So a negative delta T is going to give us a negative, is going to give us a negative Q. And if we are losing heat, if we are having heat released. So if heat is released, it is being lost to surroundings, and that is going to be a negative Q. If heat is absorbed, we are bringing it in, it's going to be a positive Q. Because if we're absorbing heat, our temperature, final temperature is going to be higher than our initial temperature. Okay. Did I say that backwards? So let me think about this. You're right, I had that backwards. Our negative Q is going to be heat absorbed. Our positive Q is going to be heat released. That's going to be positive. Sorry. Okay, that makes more sense. So let's do an example. This is not on your example sheet, but you've got space there. So the problem says if 6.5 kilojoules of heat is absorbed by a 10-gram piece of tungsten, and the temperature increases from 15 degrees Celsius to 20 degrees Celsius, what is the specific heat capacity of tungsten? This is the kind of thing that you would do if you were testing, if you had different metal samples and you weren't sure what was what. So we actually have a bunch of metal cylinders that are not labeled, so we don't know anymore what they are. I mean, the copper ones are pretty obvious, but the other ones, it's a little bit less obvious what they are. So what we could do is we could heat them up, calculate their specific heat capacity, and compare that to the table of specific heat capacities for those substances and determine which one is which. So that may be one thing that we do tomorrow. Haven't decided yet. Okay? So here's our formula, Q equals MC delta T. So what do we have that we know? Okay, we know mass. Okay, so our mass is 10 grams. Okay. Okay, our delta T, yep, is going to be, it's increasing from 15 to 20, so our final minus initial is going to be positive 5. 20 minus 15. So it goes from 15, to 20. Sorry, I wrote that incorrectly. So, all right, so our delta T is going to be positive 5 degrees Celsius. We're solving for C, right? Okay, and then 6.5, and this is going to be in joules. We've got 6.5 kilojoules. So how many joules is that? 6.5 times 10 to the third joules, right? What? Okay, this is not on that paper, but if you, here, what did I do with my other copy of it? Made another copy. I thought I made 3 copies, and I gave one to Brent, and I gave one. I swear I had another copy. What happened to it? All right, I literally don't know what happened to it. I'm sorry. Do you need do you have a notebook or a piece of paper that you can write on? Okay. Okay. Okay, so we're solving for C here. So there's obviously a couple different ways you can do this. You can rearrange the equation to put C equals, so it would be C equals Q over M delta T. And then you could put everything together. Or you could just plug the numbers into the standard equation and solve for C. I mean, whatever works best for you, for how your brain works. Okay? So our C is going to be 6.5 times 10 to the third over 10 times 5. What do you get? 130? The 10 to the third, because this says kilojoules. Okay? And our specific heat capacities are in units of joules. Okay? So, this is where, yeah. So this is going to be energy. No, you're right. Energy is absorbed. So I had it right the first time. I don't know what. Sorry. Right. So heat absorbed is going to be positive because our delta T is going to be positive. Heat released is going to be negative because our delta T is going to be negative. So this, so we have a positive delta T. That means we have a positive Q. And this is going to be, it's not a reaction really. We're just heating something. It's a process, okay? But that process is absorbing energy, right? So our Q is going to be positive the same way our delta H is going to be positive, our change in enthalpy. Okay, so we've got 130 as our answer here. What are our units for C? Now, you can go back to the slide and say, oh, it's one of these things with the degrees Celsius. But you can also just look at the units of the things that you're computing with. So our 6.5 times 10 to the third was joules, our 10 was grams, and our 5 was degrees Celsius. So there's our units. Like magic. And if you have a short answer, free response question, it probably will tell you what units it wants, or it will accept either. Okay, so, or if you're given the specific heat in a certain set of units, then those are the units that you have. And that's the units that everything else needs to be in. Okay? All right, so we've got 130 joules per gram degrees Celsius is the specific heat capacity of tungsten, according to this experiment. Okay? Sometimes you will have problems where you are given the specific heat and you're told how much heat was absorbed. If I tell you that 6.5 kilojoules of heat was absorbed by by a 10-gram piece of tungsten with a specific heat capacity of 130 joules per gram degree Celsius, how much did the temperature change? Okay, so you can, there are a lot of different formats asking for different parts of this equation. Okay. Any questions on this? Okay, so let's look at, see, now I'm annoyed that I don't have those extra copies. So I'm going to pause this. I'm going to pause it. Okay, so we're back to our example problem now, which says, I'm going to restart this a little bit. We have 50 centimeters cubed of an aqueous copper sulfate solution. It reacts with 3 grams of zinc powder. And we get our initial temperature is recorded as 21.0 degrees Celsius. What? Okay. And our T final is 43.5 degrees Celsius. Okay? And what we are determining is what is the enthalpy change for the reaction. In this case, our change in enthalpy is the same as the heat absorbed or heat released. So we're going to use our Q equals MC delta T formula to answer this question. Okay, so we have delta T. We figured out that delta T is final minus initial, which is going to be equals 22.5 degrees Celsius. When we are calculating our mass, we are looking at the volume of our solution because the majority of the mass of our solution is the water. The volume of our solution is 50 centimeters cubed, which is the same thing as 50 milliliters. Density of water is 1 gram per milliliter. And so if we have 50 milliliters of our solution, that approximates to 50 grams. That's our mass. That's what I will tell you in a second. So I'm getting there. That's the thing that I'm going to see if you have to memorize or not, or if they're going to give it to you. So so we've got our M.
Reminder, there will be a boys lacrosse meeting at 1:53 at the beginning of lunch. Again, boys lacrosse meeting for all boys and girls that play lacrosse at 1:53 at the beginning of lunch.
Okay. So we're looking for our Q, for our change in heat. Okay? So we have delta T, we have M. We are looking for C. C is the specific heat capacity. Again, we are assuming that the majority of what is changing in temperature is the water. Okay, so we're looking for C for water, and that is a constant for that substance. So for water, C is 4.18 joules per gram degree Celsius. Okay? I don't know if you need to memorize this or if it will be given to you. I will find out. Okay? 4.18 is a very high number for C. They're usually lower. We'll finish this tomorrow before we do the lab. Thanks, guys.